Chapter 12 Weather Theory. Introduction. Weather is an important factor that influences aircraft performance and flying safety. It is the state of the atmosphere at a given time and place with respect to variables, such as temperature, heat or cold, moisture, wetness or dryness, wind velocity, calm or storm, visibility, clearness or cloudiness, and barometric pressure, high or low. The term weather can also apply to adverse or destructive atmospheric conditions, such as high winds. This chapter explains basic weather theory and offers pilots background knowledge of weather principles. It is designed to help them gain a good understanding of how weather affects daily flying activities. Understanding the theories behind weather helps a pilot make sound weather decisions based on the reports and forecasts obtained from a flight service station, FSS, weather specialist, and other aviation weather services. Be it a local flight or a long cross-country flight, decisions based on weather can dramatically affect the safety of the flight. Atmosphere. The atmosphere is a blanket of air made up of a mixture of gases that surrounds the Earth and reaches almost 350 miles from the surface of the Earth. This mixture is in constant motion. If the atmosphere were visible, it might look like an ocean with swirls and eddies, rising and falling air, and waves that travel for great distances. Life on Earth is supported by the atmosphere, solar energy, and the planet's magnetic fields. The atmosphere absorbs energy from the sun, recycles water and other chemicals, and works with the electrical and magnetic forces to provide a moderate climate. The atmosphere also protects life on Earth from high-energy radiation and the frigid vacuum of space. Composition of the atmosphere. In any given volume of air, nitrogen accounts for 78% of the gases that comprise the atmosphere, while oxygen makes up 21%. Argon, carbon dioxide, and traces of other gases make up the remaining 1%. This volume of air also contains some water vapor, varying from 0 to about 5% by volume. This small amount of water vapor is responsible for major changes in the weather. The envelope of gases surrounding the Earth changes from the ground up. 4 distinct layers or spheres of the atmosphere have been identified using thermal characteristics, temperature changes, chemical composition, movement, and density. The first layer, known as the troposphere, extends from 6 to 20 kilometers, km, 4 to 12 miles, over the northern and southern poles and up to 48,000 feet, 14.5 kilometers, over the equatorial regions. The vast majority of weather, clouds, storms, and temperature variances occur within this first layer of the atmosphere. Inside the troposphere, the average temperature decreases at a rate of about 2 degrees Celsius, C, every 1,000 feet of altitude gain, and the pressure decreases at a rate of about 1 inch per 1,000 feet of altitude gain. At the top of the troposphere is a boundary known as the tropopause, which traps moisture and the associated weather in the troposphere. The altitude of the tropopause varies with latitude and with the season of the year, therefore, it takes on an elliptical shape as opposed to round. Location of the tropopause is important because it is commonly associated with the location of the jet stream and possible clear air turbulence. Above the tropopause are 3 more atmospheric levels. The first is the stratosphere, which extends from the tropopause to a height of about 160,000 feet, 50 kilometers. Little weather exists in this layer and the air remains stable, although certain types of clouds occasionally extend in it. Above the stratosphere are the mesosphere and thermosphere, which have little influence over weather. Atmospheric circulation. As noted earlier, the atmosphere is in constant motion. Certain factors combine to set the atmosphere in motion, but a major factor is the uneven heating of the Earth's surface. This heating upsets the equilibrium of the atmosphere, creating changes in air movement and atmospheric pressure. The movement of air around the surface of the Earth is called atmospheric circulation. Heating of the Earth's surface is accomplished by several processes, but in the simple convection-only model used for this discussion, the Earth is warmed by energy radiating from the sun. The process causes a circular motion that results when warm air rises and is replaced by cooler air. Warm air rises because heat causes air molecules to spread apart. As the air expands, it becomes less dense and lighter than the surrounding air. As air cools, the molecules pack together more closely, becoming denser and heavier than warm air. As a result, cool, heavy air tends to sink and replace warmer, rising air. Because the Earth has a curved surface that rotates on a tilted axis while orbiting the Sun, the equatorial regions of the Earth receive a greater amount of heat from the Sun than the polar regions. The amount of solar energy that heats the Earth depends on the time of year and the latitude of the specific region. All of these factors affect the length of time and the angle at which sunlight strikes the surface. Solar heating causes higher temperatures in equatorial areas, which causes the air to be less dense and rise. As the warm air flows toward the poles, it cools, becoming denser and sinks back toward the surface. Atmospheric pressure. The unequal heating of the Earth's surface not only modifies air density and creates circulation patterns, it also causes changes in air pressure or the force exerted by the weight of air molecules. Although air molecules are invisible, they still have weight and take up space. Imagine a sealed column of air that has a footprint of 1 square inch and is 350 miles high. It would take 14.7 pounds of effort to lift that column. This represents the air's weight. If the column is shortened, the pressure exerted at the bottom, and its weight, would be less. The weight of the shortened column of air at 18,000 feet is approximately 7.4 pounds, almost 50% that at sea level. For instance, if a bathroom scale, calibrated for sea level, were raised to 18,000 feet, the column of air weighing 14.7 pounds at sea level would be 18,000 feet shorter and would weigh approximately 7.3 pounds, 50% less than at sea level. The actual pressure at a given place and time differs with altitude, temperature, and density of the air. These conditions also affect aircraft performance, especially with regard to takeoff, rate of climb, and landings. Coriolis force. In general atmospheric circulation theory, areas of low pressure exist over the equatorial regions and areas of high pressure exist over the polar regions due to a difference in temperature. The resulting low pressure allows the high pressure air at the poles to flow along the planet's surface toward the equator. While this pattern of air circulation is correct in theory, the circulation of air is modified by several forces, the most important of which is the rotation of the Earth. The force created by the rotation of the Earth is known as the Coriolis Force. This force is not perceptible to humans as they walk around because humans move slowly and travel relatively short distances compared to the size and rotation rate of the Earth. However, the Coriolis force significantly affects motion over large distances, such as an air mass or body of water. The Coriolis force deflects air to the right in the northern hemisphere, causing it to follow a curved path instead of a straight line. The amount of deflection differs depending on the latitude. It is greatest at the poles and diminishes to 0 at the equator. The magnitude of Coriolis force also differs with the speed of the moving body. The greater the speed, the greater the deviation. In the northern hemisphere, the rotation of the Earth deflects moving air to the right and changes the general circulation pattern of the air. The Coriolis force causes the general flow to break up into 3 distinct cells in each hemisphere. In the northern hemisphere, the warm air at the equator rises upward from the surface, travels northward, and is deflected eastward by the rotation of the Earth. By the time it has traveled 1/3 of the distance from the equator to the North Pole, it is no longer moving northward, but eastward. This air cools and sinks in a belt-like area at about 30 degrees latitude, creating an area of high pressure as it sinks toward the surface. Then, it flows southward along the surface back toward the equator. Coriolis force bends the flow to the right, thus creating the northeasterly trade winds that prevail from 30 degrees latitude to the equator. Similar forces create circulation cells that encircle the Earth between 30 degrees and 60 degrees latitude and between 60 degrees and the poles. This circulation pattern results in the prevailing upper-level westerly winds in the United States. Circulation patterns are further complicated by seasonal changes, differences between the surfaces of continents and oceans, and other factors such as frictional forces caused by the topography of the Earth's surface that modify the movement of the air in the atmosphere. For example, within 2,000 feet of the ground, the friction between the surface and the atmosphere slows the moving air. The wind is diverted from its path because of the frictional force. Thus, the wind direction at the surface varies somewhat from the wind direction just a few thousand feet above the Earth. Measurement of atmosphere pressure. Atmospheric pressure historically was measured in inches of mercury, Hg, by a mercurial barometer. The barometer measures the height of a column of mercury inside a glass tube. A section of the mercury is exposed to the pressure of the atmosphere, which exerts a force on the mercury. An increase in pressure forces the mercury to rise inside the tube. When the pressure drops, mercury drains out of the tube, decreasing the height of the column. This type of barometer is typically used in a laboratory or weather observation station, is not easily transported, and difficult to read. An aneroid barometer is the standard instrument used to measure pressure. It is easier to read and transport. The aneroid barometer contains a closed vessel called an aneroid cell that contracts or expands with changes in pressure. The aneroid cell attaches to a pressure indicator with a mechanical linkage to provide pressure readings. The pressure-sensing part of an aircraft altimeter is essentially an aneroid barometer. It is important to note that due to the linkage mechanism of an aneroid barometer, it is not as accurate as a mercurial barometer. To provide a common reference, the International Standard Atmosphere, ISA, has been established. These standard conditions are the basis for certain flight instruments and most aircraft performance data. Standard sea level pressure is defined as 29.92 Hg and a standard temperature of 59 degrees Fahrenheit, 15 degrees Celsius. Atmospheric pressure is also reported in millibars, MB, with 1 Hg equal to approximately 34 MB. Standard sea level pressure is 1013.2 MB. Typical MB pressure readings range from 950.0 to 1040.0 MB. Surface charts, high and low pressure centers, and hurricane data are reported using MB. Since weather stations are located around the globe, all local barometric pressure readings are converted to a sea level pressure to provide a standard for records and reports. To achieve this, each station converts its barometric pressure by adding approximately 1 Hg for every 1,000 feet of elevation. For example, a station at 5,000 feet above sea level, with a reading of 24.92 Hg, reports a sea level pressure reading of 29.92 Hg. Using common sea level pressure readings helps ensure aircraft altimeters are set correctly, based on the current pressure readings. By tracking barometric pressure trends across a large area, weather forecasters can more accurately predict movement of pressure systems and the associated weather. For example, tracking a pattern of rising pressure at a single weather station generally indicates the approach of fair weather. Conversely, decreasing or rapidly falling pressure usually indicates approaching bad weather and, possibly, severe storms. Altitude and atmospheric pressure. As altitude increases, atmospheric pressure decreases. On average, with every 1,000 feet of increase in altitude, the atmospheric pressure decreases 1 Hg. As pressure decreases, the air becomes less dense or thinner. This is the equivalent of being at a higher altitude and is referred to as density altitude. As pressure decreases, density altitude increases and has a pronounced effect on aircraft performance. Differences in air density caused by changes in temperature result in a change in pressure. This, in turn, creates motion in the atmosphere, both vertically and horizontally, in the form of currents and wind. The atmosphere is almost constantly in motion as it strives to reach equilibrium. These never-ending air movements set up chain reactions that cause a continuing variety in the weather. Altitude and flight. Altitude affects every aspect of flight from aircraft performance to human performance. At higher altitudes, with a decreased atmospheric pressure, takeoff and landing distances are increased, while climb rates decrease. When an aircraft takes off, lift is created by the flow of air around the wings. If the air is thin, more speed is required to obtain enough lift for takeoff. Therefore, the ground run is longer. An aircraft that requires 745 feet of ground run at sea level requires more than double that at a pressure altitude of 8,000 feet. It is also true that at higher altitudes, due to the decreased density of the air, aircraft engines and propellers are less efficient. This leads to reduced rates of climb and a greater ground run for obstacle clearance. Altitude in the human body. As discussed earlier, nitrogen and other trace gases make up 79% of the atmosphere, while the remaining 21% is life-sustaining atmospheric oxygen. At sea level, atmospheric pressure is great enough to support normal growth, activity, and life. By 18,000 feet, the partial pressure of oxygen is reduced and adversely affects the normal activities and functions of the human body. The reactions of the average person become impaired at an altitude of about 10,000 feet, but for some people impairment can occur at an altitude as low as 5,000 feet. The physiological reactions to hypoxia or oxygen deprivation are insidious and affect people in different ways. These symptoms range from mild disorientation to total incapacitation, depending on body tolerance and altitude. Supplemental oxygen or cabin pressurization systems help pilots fly at higher altitudes and overcome the effects of oxygen deprivation. Wind and currents. Air flows from areas of high pressure into areas of low pressure because air always seeks out lower pressure. The combination of atmospheric pressure differences, Coriolis force, friction, and temperature differences of the air near the Earth cause two kinds of atmospheric motion: convective currents, upward and downward motion, and wind, horizontal motion. Currents and winds are important as they affect takeoff, landing, and cruise flight operations. Most importantly, currents and winds or atmospheric circulation cause weather changes. Wind patterns. In the northern hemisphere, the flow of air from areas of high to low pressure is deflected to the right and produces a clockwise circulation around an area of high pressure. This is known as anticyclonic circulation. The opposite is true of low pressure areas. The air flows toward a low and is deflected to create a counterclockwise or cyclonic circulation. High pressure systems are generally areas of dry, descending air. Good weather is typically associated with high pressure systems for this reason. Conversely, air flows into a low pressure area to replace rising air. This air usually brings increasing cloudiness and precipitation. Thus, bad weather is commonly associated with areas of low pressure. A good understanding of high and low pressure wind patterns can be of great help when planning a flight because a pilot can take advantage of beneficial tailwinds. When planning a flight from west to east, favorable winds would be encountered along the northern side of a high pressure system or the southern side of a low pressure system. On the return flight, the most favorable winds would be along the southern side of the same high pressure system or the northern side of a low pressure system. An added advantage is a better understanding of what type of weather to expect in a given area along a route of flight based on the prevailing areas of highs and lows. While the theory of circulation and wind patterns is accurate for large-scale atmospheric circulation, it does not take into account changes to the circulation on a local scale. Local conditions, geological features, and other anomalies can change the wind direction and speed close to the Earth's surface. Convective currents. Plowed ground, rocks, sand, and barren land absorb solar energy quickly and can therefore give off a large amount of heat. Whereas, water, trees, and other areas of vegetation tend to more slowly absorb heat and give off heat. The resulting uneven heating of the air creates small areas of local circulation called convective currents. Convective currents cause the bumpy, turbulent air sometimes experienced when flying at lower altitudes during warmer weather. On a low-altitude flight over varying surfaces, updrafts are likely to occur over pavement or barren places, and downdrafts often occur over water or expansive areas of vegetation like a group of trees. Typically, these turbulent conditions can be avoided by flying at higher altitudes, even above cumulus cloud layers. Convective currents are particularly noticeable in areas with a landmass directly adjacent to a large body of water, such as an ocean, large lake, or other appreciable area of water. During the day, land heats faster than water, so the air over the land becomes warmer and less dense. It rises and is replaced by cooler, denser air flowing in from over the water. This causes an onshore wind called a sea breeze. Conversely, at night land cools faster than water, as does the corresponding air. In this case, the warmer air over the water rises and is replaced by the cooler, denser air from the land, creating an offshore wind called a land breeze. This reverses the local wind circulation pattern. Convective currents can occur anywhere there is an uneven heating of the Earth's surface. Convective currents close to the ground can affect a pilot's ability to control the aircraft. For example, on final approach, the rising air from terrain devoid of vegetation sometimes produces a ballooning effect that can cause a pilot to overshoot the intended landing spot. On the other hand, an approach over a large body of water or an area of thick vegetation tends to create a sinking effect that can cause an unwary pilot to land short of the intended landing spot. Effect of obstructions on wind. Another atmospheric hazard exists that can create problems for pilots. Obstructions on the ground affect the flow of wind and can be an unseen danger. Ground topography and large buildings can break up the flow of the wind and create wind gusts that change rapidly in direction and speed. These obstructions range from man-made structures, like hangars, to large natural obstructions, such as mountains, bluffs, or canyons. It is especially important to be vigilant when flying in or out of airports that have large buildings or natural obstructions located near the runway. The intensity of the turbulence associated with ground obstructions depends on the size of the obstacle and the primary velocity of the wind. This can affect the takeoff and landing performance of any aircraft and can present a very serious hazard. During the landing phase of flight, an aircraft, sea breeze and land breeze wind circulation patterns, currents generated by varying surface conditions, may drop in due to the turbulent air and be too low to clear obstacles during the approach. This same condition is even more noticeable when flying in mountainous regions. While the wind flows smoothly up the windward side of the mountain and the upward currents help to carry an aircraft over the peak of the mountain, the wind on the leeward side does not act in a similar manner. As the air flows down the leeward side of the mountain, the air follows the contour of the terrain and is increasingly turbulent. This tends to push an aircraft into the side of a mountain. The stronger the wind, the greater the downward pressure and turbulence become. Due to the effect terrain has on the wind in valleys or canyons, downdrafts can be severe. Before conducting a flight in or near mountainous terrain, it is helpful for a pilot unfamiliar with a mountainous area to get a checkout with a mountain-qualified flight instructor. Low-level wind shear. Wind shear is a sudden, drastic change in wind speed and/or direction over a very small area. Wind shear can subject an aircraft to violent updrafts and downdrafts, as well as abrupt changes to the horizontal movement of the aircraft. While wind shear can occur at any altitude, low-level wind shear is especially hazardous due to the proximity of an aircraft to the ground. Low-level wind shear is commonly associated with passing frontal systems, thunderstorms, temperature inversions, and strong upper-level winds, greater than 25 knots. Wind shear is dangerous to an aircraft. It can rapidly change the performance of the aircraft and disrupt the normal flight attitude. For example, a tailwind quickly changing to a headwind causes an increase in airspeed and performance. Conversely, a headwind changing to a tailwind causes a decrease in airspeed and performance. In either case, a pilot must be prepared to react immediately to these changes to maintain control of the aircraft. The most severe type of low-level wind shear, a microburst, is associated with convective precipitation into dry air at cloud base. Microburst activity may be indicated by an intense rain shaft at the surface, but virga at cloud base and a ring of blowing dust is often the only visible clue. A typical microburst has a horizontal diameter of 1 to 2 miles and a nominal depth of 1,000 feet. The lifespan of a microburst is about 5 to 15 minutes, during which time it can produce downdrafts of up to 6,000 feet per minute, (fpm), and headwind losses of 30 to 90 knots, seriously degrading performance. It can also produce strong turbulence and hazardous wind direction changes. Consider figure 12 to 17. During an inadvertent takeoff into a microburst, the plane may first experience a performance-increasing headwind, 1, followed by performance-decreasing downdrafts, 2, followed by a rapidly increasing tailwind, 3. This can result in terrain impact or flight dangerously close to the ground, 4. An encounter during approach involves the same sequence of wind changes and could force the plane to the ground short of the runway. The FAA has made a substantial investment in microburst accident prevention. The totally redesigned LLWAS-NA, the TDWR, and the OSR 9 WSP are skillful microburst alerting systems installed at major airports. These 3 systems were extensively evaluated over a 3-year period. Each was seen to issue very few false alerts and to detect microburst well above the 90% detection requirement established by Congress. Many flights involve airports that lack microburst alert equipment, so the FAA has also prepared wind shear training material. Advisory Circular AC 0054, FAA Pilot Wind Shear Guide. Included is information on how to recognize the risk of a microburst encounter, how to avoid an encounter, and the best flight strategy for successful escape should an encounter occur. It is important to remember that wind shear can affect any flight and any pilot at any altitude. While wind shear may be reported, it often remains undetected and is a silent danger to aviation. Always be alert to the possibility of wind shear, especially when flying in and around thunderstorms and frontal systems. Wind and pressure representation on surface weather maps. Surface weather maps provide information about fronts, areas of high and low pressure, and surface winds and pressures for each station. This type of weather map allows pilots to see the locations of fronts and pressure systems, but more importantly, it depicts the wind and pressure at the surface for each location. For more information on surface analysis and weather depiction charts, see Chapter 13, Aviation Weather Services. Wind conditions are reported by an arrow attached to the station location circle. The station circle represents the head of the arrow, with the arrow pointing in the direction from which the wind is blowing. Winds are described by the direction from which they blow, thus a northwest wind means that the wind is blowing from the northwest toward the southeast. The speed of the wind is depicted by barbs or pennants placed on the wind line. Each barb represents a speed of 10 knots, while half a barb is equal to 5 knots, and a pennant is equal to 50 knots. The pressure for each station is recorded on the weather chart and is shown in MB. Isobars are lines drawn on the chart to depict lines of equal pressure. These lines result in a pattern that reveals the pressure gradient or change in pressure over distance. Isobars are similar to contour lines on a topographic map that indicate terrain altitudes and slope steepness. For example, isobars that are closely spaced indicate a steep pressure gradient and strong winds prevail. Shallow gradients, on the other hand, are represented by isobars that are spaced far apart and are indicative of light winds. Isobars help identify low and high pressure systems, as well as the location of ridges and troughs. A high is an area of high pressure surrounded by lower pressure. A low is an area of low pressure surrounded by higher pressure. A ridge is an elongated area of high pressure, and a trough is an elongated area of low pressure. Isobars furnish valuable information about winds in the first few thousand feet above the surface. Close to the ground, wind direction is modified by the friction and wind speed decreases due to friction with the surface. At levels 2,000 to 3,000 feet above the surface, however, the speed is greater and the direction becomes more parallel to the isobars. Generally, the wind 2,000 feet above ground level, AGL, is 20 degrees to 40 degrees to the right of surface winds, and the wind speed is greater. The change of wind direction is greatest over rough terrain and least over flat surfaces, such as open water. In the absence of winds aloft information, this rule of thumb allows for a rough estimate of the wind conditions a few thousand feet above the surface. Atmospheric stability. The stability of the atmosphere depends on its ability to resist vertical motion. A stable atmosphere makes vertical movement difficult, and small vertical disturbances dampen out and disappear. In an unstable atmosphere, small vertical air movements tend to become larger, resulting in turbulent airflow and convective activity. Instability can lead to significant turbulence, extensive vertical clouds, and severe weather. Rising air expands and cools due to the decrease in air pressure as altitude increases. The opposite is true of descending air. As atmospheric pressure increases, the temperature of descending air increases as it is compressed. Adiabatic heating and adiabatic cooling are terms used to describe this temperature change. The adiabatic process takes place in all upward and downward moving air. When air rises into an area of lower pressure, it expands to a larger volume. As the molecules of air expand, the temperature of the air lowers. As a result, when a parcel of air rises, pressure decreases, volume increases, and temperature decreases. When air descends, the opposite is true. The rate at which temperature decreases with an increase in altitude is referred to as its lapse rate. As air ascends through the atmosphere, the average rate of temperature change is 2 degrees Celsius, 3.5 degrees Fahrenheit, per 1,000 feet. Since water vapor is lighter than air, moisture decreases air density, causing it to rise. Conversely, as moisture decreases, air becomes denser and tends to sink. Since moist air cools at a slower rate, it is generally less stable than dry air since the moist air must rise higher before its temperature cools to that of the surrounding air. The dry adiabatic lapse rate, unsaturated air, is 3 degrees Celsius, 5.4 degrees Fahrenheit, per 1,000 feet. The moist adiabatic lapse rate varies from 1.1 degrees Celsius to 2.8 degrees Celsius, 2 degrees Fahrenheit to 5 degrees Fahrenheit, per 1,000 feet. The combination of moisture and temperature determine the stability of the air and the resulting weather. Cool, dry air is very stable and resists vertical movement, which leads to good and generally clear weather. The greatest instability occurs when the air is moist and warm, as it is in the tropical regions in the summer. Typically, thunderstorms appear on a daily basis in these regions due to the instability of the surrounding air. Inversion. As air rises and expands in the atmosphere, the temperature decreases. There is an atmospheric anomaly that can occur, however, that changes this typical pattern of atmospheric behavior. When the temperature of the air rises with altitude, a temperature inversion exists. Inversion layers are commonly shallow layers of smooth, stable air close to the ground. The temperature of the air increases with altitude to a certain point, which is the top of the inversion. The air at the top of the layer acts as a lid, keeping weather and pollutants trapped below. If the relative humidity of the air is high, it can contribute to the formation of clouds, fog, haze, or smoke, resulting in diminished visibility in the inversion layer. Surface-based temperature inversions occur on clear, cool nights when the air close to the ground is cooled by the lowering temperature of the ground. The air within a few hundred feet of the surface becomes cooler than the air above it. Frontal inversions occur when warm air spreads over a layer of cooler air, or cooler air is forced under a layer of warmer air. Moisture and temperature. The atmosphere, by nature, contains moisture in the form of water vapor. The amount of moisture present in the atmosphere is dependent upon the temperature of the air. Every 20 degrees Fahrenheit increase in temperature doubles the amount of moisture the air can hold. Conversely, a decrease of 20 degrees Fahrenheit cuts the capacity in half. Water is present in the atmosphere in three states: liquid, solid, and gaseous. All three forms can readily change to another, and all are present within the temperature ranges of the atmosphere. As water changes from one state to another, an exchange of heat takes place. These changes occur through the processes of evaporation, sublimation, condensation, deposition, melting, or freezing. However, water vapor is added into the atmosphere only by the processes of evaporation and sublimation. Evaporation is the changing of liquid water to water vapor. As water vapor forms, it absorbs heat from the nearest available source. This heat exchange is known as the latent heat of evaporation. A good example is the evaporation of human perspiration. The net effect is a cooling sensation as heat is extracted from the body. Similarly, sublimation is the changing of ice directly to water vapor, completely bypassing the liquid stage. Though dry ice is not made of water, but rather carbon dioxide, it demonstrates the principle of sublimation when a solid turns directly into vapor. Relative humidity. Humidity refers to the amount of water vapor present in the atmosphere at a given time. Relative humidity is the actual amount of moisture in the air compared to the total amount of moisture the air could hold at that temperature. For example, if the current relative humidity is 65%, the air is holding 65% of the total amount of moisture that it is capable of holding at that temperature and pressure. While much of the western United States rarely sees days of high humidity, relative humidity readings of 75 to 90% are not uncommon in the southern United States during warmer months. Temperature-dew point relationship. The relationship between dew point and temperature defines the concept of relative humidity. The dew point, given in degrees, is the temperature at which the air can hold no more moisture. When the temperature of the air is reduced to the dew point, the air is completely saturated and moisture begins to condense out of the air in the form of fog, dew, frost, clouds, rain, or snow. As moist, unstable air rises, clouds often form at the altitude where temperature and dew point reach the same value. When lifted, unsaturated air cools at a rate of 5.4 degrees Fahrenheit per 1,000 feet and the dew point temperature decreases at a rate of 1 degree Fahrenheit per 1,000 feet. This results in a convergence of temperature and dew point at a rate of 4.4 degrees Fahrenheit. Apply the convergence rate to the reported temperature and dew point to determine the height of the cloud base. Given temperature, T, equals 85 degrees Fahrenheit dew point, dP, equals 71 degrees Fahrenheit convergence rate, CR, equals 4.4 degrees T, dP equals temperature dew point spread, TDS divided by CR equals XX times 1,000 feet equals height of cloud base AGL. Example: 85 degrees Fahrenheit to 71 degrees Fahrenheit equals 14 degrees Fahrenheit. 14 degrees Fahrenheit divided by 4.4 degrees Fahrenheit equals 3.18. 3.18 times 1000 equals 3,180 feet AGL. The height of the cloud base is 3,180 feet AGL. Explanation: with an outside air temperature, OAT, of 85 degrees Fahrenheit at the surface and dew point at the surface of 71 degrees Fahrenheit, the spread is 14 degrees. Divide the temperature dew point spread by the convergence rate of 4.4 degrees Fahrenheit, and multiply by 1000 to determine the approximate height of the cloud base. Methods by which air reaches the saturation point. If air reaches the saturation point while temperature and dew point are close together, it is highly likely that fog, low clouds, and precipitation will form. There are four methods by which air can reach the saturation point. First, when warm air moves over a cold surface, the air temperature drops and reaches the saturation point. Second, the saturation point may be reached when cold air and warm air mix. Third, when air cools at night through contact with the cooler ground, air reaches its saturation point. The fourth method occurs when air is lifted or is forced upward in the atmosphere. As air rises, it uses heat energy to expand. As a result, the rising air loses heat rapidly. Unsaturated air loses heat at a rate of 3.0 degrees Celsius, 5.4 degrees Fahrenheit, for every 1,000 feet of altitude gain. No matter what causes the air to reach its saturation point, saturated air brings clouds, rain, and other critical weather situations. Dew and frost. On cool, clear, calm nights, the temperature of the ground and objects on the surface can cause temperatures of the surrounding air to drop below the dew point. When this occurs, the moisture in the air condenses and deposits itself on the ground, buildings, and other objects like cars and aircraft. This moisture is known as dew and sometimes can be seen on grass and other objects in the morning. If the temperature is below freezing, the moisture is deposited in the form of frost. While dew poses no threat to an aircraft, frost poses a definite flight safety hazard. Frost disrupts the flow of air over the wing and can drastically reduce the production of lift. It also increases drag, which when combined with lowered lift production, can adversely affect the ability to take off. An aircraft must be thoroughly cleaned and free of frost prior to beginning a flight. Fog. Fog is a cloud that is on the surface. It typically occurs when the temperature of air near the ground is cooled to the air's dew point. At this point, water vapor in the air condenses and becomes visible in the form of fog. Fog is classified according to the manner in which it forms and is dependent upon the current temperature and the amount of water vapor in the air. On clear nights, with relatively little to no wind present, radiation fog may develop. Usually, it forms in low-lying areas like mountain valleys. This type of fog occurs when the ground cools rapidly due to terrestrial radiation, and the surrounding air temperature reaches its dew point. As the sun rises and the temperature increases, radiation fog lifts and eventually burns off. Any increase in wind also speeds the dissipation of radiation fog. If radiation fog is less than 20 feet thick, it is known as ground fog. When a layer of warm, moist air moves over a cold surface, advection fog is likely to occur. Unlike radiation fog, wind is required to form advection fog. Winds of up to 15 knots allow the fog to form and intensify. Above a speed of 15 knots, the fog usually lifts and forms low stratus clouds. Advection fog is common in coastal areas where sea breezes can blow the air over cooler landmasses. Upslope fog occurs when moist, stable air is forced up sloping land features like a mountain range. This type of fog also requires wind for formation and continued existence. Upslope and advection fog, unlike radiation fog, may not burn off with the morning sun but instead can persist for days. They can also extend to greater heights than radiation fog. Steam fog or sea smoke forms when cold, dry air moves over warm water. As the water evaporates, it rises and resembles smoke. This type of fog is common over bodies of water during the coldest times of the year. Low-level turbulence and icing are commonly associated with steam fog. Ice fog occurs in cold weather when the temperature is much below freezing and water vapor forms directly into ice crystals. Conditions favorable for its formation are the same as for radiation fog except for cold temperature, usually -25 degrees Fahrenheit or colder. It occurs mostly in the Arctic regions but is not unknown in middle latitudes during the cold season. Clouds. Clouds are visible indicators and are often indicative of future weather. For clouds to form, there must be adequate water vapor and condensation nuclei, as well as a method by which the air can be cooled. When the air cools and reaches its saturation point, the invisible water vapor changes into a visible state. Through the processes of deposition, also referred to as sublimation, and condensation, moisture condenses or sublimates onto minuscule particles of matter like dust, salt, and smoke known as condensation nuclei. The nuclei are important because they provide a means for the moisture to change from one state to another. Cloud type is determined by its height, shape, and characteristics. They are classified according to the height of their bases as low, middle, or high clouds, as well as clouds with vertical development. Low clouds are those that form near the Earth's surface and extend up to about 6,500 feet AGL. They are made primarily of water droplets but can include supercooled water droplets that induce hazardous aircraft icing. Typical low clouds are stratus, stratocumulus, and nimbostratus. Fog is also classified as a type of low cloud formation. Clouds in this family create low ceilings, hamper visibility, and can change rapidly. Because of this, they influence flight planning and can make visual flight rules, VFR, flight impossible. Middle clouds form around 6,500 feet AGL and extend up to 20,000 feet AGL. They are composed of water, ice crystals, and supercooled water droplets. Typical middle-level clouds include altostratus and altocumulus. These types of clouds may be encountered on cross-country flights at higher altitudes. Altostratus clouds can produce turbulence and may contain moderate icing. Altocumulus clouds, which usually form when altostratus clouds are breaking apart, also may contain light turbulence and icing. High clouds form above 20,000 feet AGL and usually form only in stable air. They are made up of ice crystals and pose no real threat of turbulence or aircraft icing. Typical high-level clouds are cirrus, cirrostratus, and cirrocumulus. Clouds with extensive vertical development are cumulus clouds that build vertically into towering cumulus or cumulonimbus clouds. The bases of these clouds form in the low to middle cloud base region but can extend into high-altitude cloud levels. Towering cumulus clouds indicate areas of instability in the atmosphere, and the air around and inside them is turbulent. These types of clouds often develop into cumulonimbus clouds or thunderstorms. Cumulonimbus clouds contain large amounts of moisture and unstable air, and usually produce hazardous weather phenomena, such as lightning, hail, tornadoes, gusty winds, and wind shear. These extensive vertical clouds can be obscured by other cloud formations and are not always visible from the ground or while in flight. When this happens, these clouds are said to be embedded, hence the term, embedded thunderstorms. To pilots, the cumulonimbus cloud is perhaps the most dangerous cloud type. It appears individually or in groups and is known as either an air mass or orographic thunderstorm. Heating of the air near the Earth's surface creates an air mass thunderstorm. The upslope motion of air in the mountainous regions causes orographic thunderstorms. Cumulonimbus clouds that form in a continuous line are non-frontal bands of thunderstorms or squall lines. Since rising air currents cause cumulonimbus clouds, they are extremely turbulent and pose a significant hazard to flight safety. For example, if an aircraft enters a thunderstorm, the aircraft could experience updrafts and downdrafts that exceed 3,000 fpm. In addition, thunderstorms can produce large hailstones, damaging lightning, tornadoes, and large quantities of water, all of which are potentially hazardous to aircraft. Cloud classification can be further broken down into specific cloud types according to the outward appearance and cloud composition. Knowing these terms can help a pilot identify visible clouds. The following is a list of cloud classifications. Cumulus, heaped or piled clouds. Stratus, formed in layers. Cirrus, ringlets, fibrous clouds, also high-level clouds above 20,000 feet. Castellanus, common base with separate vertical development, castle-like. Lenticularis, lens-shaped, formed over mountains in strong winds. Nimbus, rain-bearing clouds. Fracto, ragged or broken. Alto, middle-level clouds existing at 5,000 to 20,000 feet. Ceiling. For aviation purposes, a ceiling is the lowest layer of clouds reported as being broken or overcast, or the vertical visibility into an obscuration like fog or haze. Clouds are reported as broken when 5/8 to 7/8 of the sky is covered with clouds. Overcast means the entire sky is covered with clouds. Current ceiling information is reported by the Aviation Routine Weather Report, METAR, and automated weather stations of various types. Visibility. Closely related to cloud cover and reported ceilings is visibility information. Visibility refers to the greatest horizontal distance at which prominent objects can be viewed with the naked eye. Current visibility is also reported in METAR and other aviation weather reports, as well as by automated weather systems. Visibility information, as predicted by meteorologists, is available for a pilot during a pre-flight weather briefing. Precipitation. Precipitation refers to any type of water particles that form in the atmosphere and fall to the ground. It has a profound impact on flight safety. Depending on the form of precipitation, it can reduce visibility, create icing situations, and affect landing and takeoff performance of an aircraft. Precipitation occurs because water or ice particles in clouds grow in size until the atmosphere can no longer support them. It can occur in several forms as it falls toward the Earth, including drizzle, rain, ice pellets, hail, snow, and ice. Drizzle is classified as very small water droplets, smaller than 0.02 inches in diameter. Drizzle usually accompanies fog or low stratus clouds. Water droplets of larger size are referred to as rain. Rain that falls through the atmosphere but evaporates prior to striking the ground is known as virga. Freezing rain and freezing drizzle occur when the temperature of the surface is below freezing. The rain freezes on contact with the cooler surface. If rain falls through a temperature inversion, it may freeze as it passes through the underlying cold air and fall to the ground in the form of ice pellets. Ice pellets are an indication of a temperature inversion in that freezing rain exists at a higher altitude. In the case of hail, freezing water droplets are carried up and down by drafts inside cumulonimbus clouds, growing larger in size as they come in contact with more moisture. Once the updrafts can no longer hold the freezing water, it falls to the earth in the form of hail. Hail can be pea-sized, or it can grow as large as 5 inches in diameter, larger than a softball. Snow is precipitation in the form of ice crystals that falls at a steady rate or in snow showers that begin, change in intensity, and end rapidly. Snow also varies in size, from very small grains to large flakes. Snow grains are the equivalent of drizzle in size. Precipitation in any form poses a threat to safety of flight. Often, precipitation is accompanied by low ceilings and reduced visibility. Aircraft that have ice, snow, or frost on their surfaces must be carefully cleaned prior to beginning a flight because of the possible airflow disruption and loss of lift. Rain can contribute to water in the fuel tanks. Precipitation can create hazards on the runway surface itself, making takeoffs and landings difficult, if not impossible, due to snow, ice, or pooling water and very slick surfaces. Air masses. Air masses are classified according to the regions where they originate. They are large bodies of air that take on the characteristics of the surrounding area or source region. A source region is typically an area in which the air remains relatively stagnant for a period of days or longer. During this time of stagnation, the air mass takes on the temperature and moisture characteristics of the source region. Areas of stagnation can be found in polar regions, tropical oceans, and dry deserts. Air masses are generally identified as polar or tropical based on temperature characteristics and maritime or continental based on moisture content. A continental polar air mass forms over a polar region and brings cool, dry air with it. Maritime tropical air masses form over warm tropical waters like the Caribbean Sea and bring warm, moist air. As the air mass moves from its source region and passes over land or water, the air mass is subjected to the varying conditions of the land or water which modify the nature of the air mass. An air mass passing over a warmer surface is warmed from below, and convective currents form, causing the air to rise. This creates an unstable air mass with good surface visibility. Moist, unstable air causes cumulus clouds, showers, and turbulence to form. Conversely, an air mass passing over a colder surface does not form convective currents but instead creates a stable air mass with poor surface visibility. The poor surface visibility is due to the fact that smoke, dust, and other particles cannot rise out of the air mass and are instead trapped near the surface. A stable air mass can produce low stratus clouds and fog. Fronts. As an air mass moves across bodies of water and land, it eventually comes in contact with another air mass with different characteristics. The boundary layer between two types of air masses is known as a front. An approaching front of any type always means changes to the weather are imminent. There are 4 types of fronts that are named according to the temperature of the advancing air relative to the temperature of the air it is replacing. Warm, cold, stationary, occluded. Any discussion of frontal systems must be tempered with the knowledge that no 2 fronts are the same. However, generalized weather conditions are associated with a specific type of front that helps identify the front. Warm front. A warm front occurs when a warm mass of air advances and replaces a body of colder air. Warm fronts move slowly, typically 10 to 25 miles per hour, mph. The slope of the advancing front slides over the top of the cooler air and gradually pushes it out of the area. Warm fronts contain warm air that often has very high humidity. As the warm air is lifted, the temperature drops and condensation occurs. Generally, prior to the passage of a warm front, cirriform or stratiform clouds, along with fog, can be expected to form along the frontal boundary. In the summer months, cumulonimbus clouds, thunderstorms, are likely to develop. Light to moderate precipitation is probable, usually in the form of rain, sleet, snow, or drizzle, accentuated by poor visibility. The wind blows from the south-southeast, and the outside temperature is cool or cold with an increasing dew point. Finally, as the warm front approaches, the barometric pressure continues to fall until the front passes completely. During the passage of a warm front, stratiform clouds are visible and drizzle may be falling. The visibility is generally poor, but improves with variable winds. The temperature rises steadily from the inflow of relatively warmer air. For the most part, the dew point remains steady and the pressure levels off. After the passage of a warm front, stratocumulus clouds predominate and rain showers are possible. The visibility eventually improves, but hazy conditions may exist for a short period after passage. The wind blows from the south-southwest. With warming temperatures, the dew point rises and then levels off. There is generally a slight rise in barometric pressure, followed by a decrease of barometric pressure. Flight toward an approaching warm front. By studying a typical warm front, much can be learned about the general patterns and atmospheric conditions that exist when a warm front is encountered in flight. Figure 12 to 25 depicts a warm front advancing eastward from St. Louis, Missouri, toward Pittsburgh, Pennsylvania during a flight from Pittsburgh to St. Louis. At the time of departure from Pittsburgh, the weather is good VFR with a scattered layer of cirrus clouds at 15,000 feet. As the flight progresses westward to Columbus and closer to the oncoming warm front, the clouds deepen and become increasingly stratiform in appearance with a ceiling of 6,000 feet. The visibility decreases to 6 miles in haze with a falling barometric pressure. Approaching Indianapolis, the weather deteriorates to broken clouds at 2,000 feet with 3 miles visibility and rain. With the temperature and dew point the same, fog is likely to develop. At St. Louis, the sky is overcast with low clouds and drizzle and the visibility is 1 mile. Beyond Indianapolis, the ceiling and visibility are too low to continue VFR. Therefore, it would be wise to remain in Indianapolis until the warm front passes, which may take up to 2 days. Cold front. A cold front occurs when a mass of cold, dense, and stable air advances and replaces a body of warmer air. Cold fronts move more rapidly than warm fronts, progressing at a rate of 25 to 30 miles per hour. However, extreme cold fronts have been recorded moving at speeds of up to 60 miles per hour. A typical cold front moves in a manner opposite that of a warm front. It is so dense, it stays close to the ground and acts like a snowplow, sliding under the warmer air and forcing the less dense air aloft. The rapidly ascending air causes the temperature to decrease suddenly, forcing the creation of clouds. The type of clouds that form depends on the stability of the warmer air mass. A cold front in the northern hemisphere is normally oriented in a northeast to southwest manner and can be several hundred miles long, encompassing a large area of land. Prior to the passage of a typical cold front, cirriform or towering cumulus clouds are present, and cumulonimbus clouds may develop. Rain showers may also develop due to the rapid development of clouds. A high dew point and falling barometric pressure are indicative of imminent cold front passage. As the cold front passes, towering cumulus or cumulonimbus clouds continue to dominate the sky. Depending on the intensity of the cold front, heavy rain showers form and may be accompanied by lightning, thunder, and/or hail. More severe cold fronts can also produce tornadoes. During cold front passage, the visibility is poor with winds variable and gusty, and the temperature and dew point drop rapidly. A quickly falling barometric pressure bottoms out during frontal passage, then begins a gradual increase. After frontal passage, the towering cumulus and cumulonimbus clouds begin to dissipate to cumulus clouds with a corresponding decrease in the precipitation. Good visibility eventually prevails with the winds from the west-northwest. Temperatures remain cooler and the barometric pressure continues to rise. Fast-moving cold front. Fast-moving cold fronts are pushed by intense pressure systems far behind the actual front. The friction between the ground and the cold front retards the movement of the front and creates a steeper frontal surface. This results in a very narrow band of weather, concentrated along the leading edge of the front. If the warm air being overtaken by the cold front is relatively stable, overcast skies and rain may occur for some distance behind the front. If the warm air is unstable, scattered thunderstorms and rain showers may form. A continuous line of thunderstorms, or squall line, may form along or ahead of the front. Squall lines present a serious hazard to pilots as squall-type thunderstorms are intense and move quickly. Behind a fast-moving cold front, the skies usually clear rapidly, and the front leaves behind gusty, turbulent winds and colder temperatures. Flight toward an approaching cold front. Like warm fronts, not all cold fronts are the same. Examining a flight toward an approaching cold front, pilots can get a better understanding of the type of conditions that can be encountered in flight. Figure 12 to 26 depicts a flight from Pittsburgh, Pennsylvania, toward St. Louis, Missouri. At the time of departure from Pittsburgh, the weather is VFR with 3 miles visibility in smoke and a scattered layer of clouds at 3,500 feet. As the flight progresses westward to Columbus and closer to the oncoming cold front, the clouds show signs of vertical development with a broken layer at 2,500 feet. The visibility is 6 miles in haze with a falling barometric pressure. Approaching Indianapolis, the weather has deteriorated to overcast clouds at 1,000 feet and 3 miles visibility with thunderstorms and heavy rain showers. At St. Louis, the weather gets better with scattered clouds at 1,000 feet and a 10-mile visibility. A pilot using sound judgment based on the knowledge of frontal conditions will likely remain in Indianapolis until the front has passed. Trying to fly below a line of thunderstorms or a squall line is hazardous, and flight over the top of or around the storm is not an option. Thunderstorms can extend up to well over the capability of small airplanes and can extend in a line for 300 to 500 miles. Comparison of cold and warm fronts. Warm fronts and cold fronts are very different in nature, as are the hazards associated with each front. They vary in speed, composition, weather phenomenon, and prediction. Cold fronts, which move at 20 to 35 miles per hour, travel faster than warm fronts, which move at only 10 to 25 miles per hour. Cold fronts also possess a steeper frontal slope. Violent weather activity is associated with cold fronts, and the weather usually occurs along the frontal boundary, not in advance. However, squall lines can form during the summer months as far as 200 miles in advance of a strong cold front. Whereas warm fronts bring low ceilings, poor visibility, and rain, cold fronts bring sudden storms, gusty winds, turbulence, and sometimes hail or tornadoes. Cold fronts are fast approaching with little or no warning, and they bring about a complete weather change in just a few hours. The weather clears rapidly after passage and drier air with unlimited visibilities prevail. Warm fronts, on the other hand, provide advance warning of their approach and can take days to pass through a region. Wind shifts. Wind around a high-pressure system rotates clockwise, while low-pressure winds rotate counterclockwise. When two high-pressure systems are adjacent, the winds are almost in direct opposition to each other at the point of contact. Fronts are the boundaries between two areas of high pressure, and therefore, wind shifts are continually occurring within a front. Shifting wind direction is most pronounced in conjunction with cold fronts. Stationary front. When the forces of two air masses are relatively equal, the boundary or front that separates them remains stationary and influences the local weather for days. This front is called a stationary front. The weather associated with a stationary front is typically a mixture that can be found in both warm and cold fronts. Occluded front. An occluded front occurs when a fast-moving cold front catches up with a slow-moving warm front. As the occluded front approaches, warm front weather prevails but is immediately followed by cold front weather. There are two types of occluded fronts that can occur, and the temperatures of the colliding frontal systems play a large part in defining the type of front and the resulting weather. A cold front occlusion occurs when a fast-moving cold front is colder than the air ahead of the slow-moving warm front. When this occurs, the cold air replaces the cool air and forces the warm front aloft into the atmosphere. Typically, the cold front occlusion creates a mixture of weather found in both warm and cold fronts, providing the air is relatively stable. A warm front occlusion occurs when the air ahead of the warm front is colder than the air of the cold front. When this is the case, the cold front rides up and over the warm front. If the air forced aloft by the warm front occlusion is unstable, the weather is more severe than the weather found in a cold front occlusion. Embedded thunderstorms, rain, and fog are likely to occur. Figure 12 to 27 depicts a cross-section of a typical cold front occlusion. The warm front slopes over the prevailing cooler air and produces the warm front-type weather. Prior to the passage of the typical occluded front, cirriform and stratiform clouds prevail, light to heavy precipitation falls, visibility is poor, dew point is steady, and barometric pressure drops. During the passage of the front, nimbostratus and cumulonimbus clouds predominate, and towering cumulus clouds may also form. Light to heavy precipitation falls, visibility is poor, winds are variable, and the barometric pressure levels off. After the passage of the front, nimbostratus and altostratus clouds are visible, precipitation decreases, and visibility improves. Thunderstorms. A thunderstorm makes its way through three distinct stages before dissipating. It begins with the cumulus stage, in which lifting action of the air begins. If sufficient moisture and instability are present, the clouds continue to increase in vertical height. Continuous, strong updrafts prohibit moisture from falling. Within approximately 15 minutes, the thunderstorm reaches the mature stage, which is the most violent time period of the thunderstorm's life cycle. At this point, drops of moisture, whether rain or ice, are too heavy for the cloud to support and begin falling in the form of rain or hail. This creates a downward motion of the air. Warm, rising air, cool, precipitation-induced descending air, and violent turbulence all exist within and near the cloud. Below the cloud, the down-rushing air increases surface winds and decreases the temperature. Once the vertical motion near the top of the cloud slows down, the top of the cloud spreads out and takes on an anvil-like shape. At this point, the storm enters the dissipating stage. This is when the downdrafts spread out and replace the updrafts needed to sustain the storm. It is impossible to fly over thunderstorms in light aircraft. Severe thunderstorms can punch through the tropopause and reach staggering heights of 50,000 to 60,000 feet depending on latitude. Flying under thunderstorms can subject aircraft to rain, hail, damaging lightning, and violent turbulence. A good rule of thumb is to circumnavigate thunderstorms identified as severe or giving an extreme radar echo by at least 20 nautical miles (nm), since hail may fall for miles outside of the clouds. If flying around a thunderstorm is not an option, stay on the ground until it passes. For a thunderstorm to form, the air must have sufficient water vapor, an unstable lapse rate, and an initial lifting action to start the storm process. Some storms occur at random in unstable air, last for only an hour or two, and produce only moderate wind gusts and rainfall. These are known as air mass thunderstorms and are generally a result of surface heating. Steady-state thunderstorms are associated with weather systems, fronts, converging winds, and troughs aloft force upward motion spawning these storms that often form into squall lines. In the mature stage, updrafts become stronger and last much longer than in air mass storms, hence the name steady state. Knowledge of thunderstorms and the hazards associated with them is critical to the safety of flight. Hazards. All thunderstorms have conditions that are a hazard to aviation. These hazards occur in numerous combinations. While not every thunderstorm contains all hazards, it is not possible to visually determine which hazards a thunderstorm contains. Squall line. A squall line is a narrow band of active thunderstorms. Often it develops on or ahead of a cold front in moist, unstable air, but it may develop in unstable air far removed from any front. The line may be too long to detour easily and too wide and severe to penetrate. It often contains steady-state thunderstorms and presents the single most intense weather hazard to aircraft. It usually forms rapidly, generally reaching maximum intensity during the late afternoon and the first few hours of darkness. Tornadoes. The most violent thunderstorms draw air into their cloud bases with great vigor. If the incoming air has any initial rotating motion, it often forms an extremely concentrated vortex from the surface well into the cloud. Meteorologists have estimated that wind in such a vortex can exceed 200 knots with pressure inside the vortex quite low. The strong winds gather dust and debris and the low pressure generates a funnel-shaped cloud extending downward from the cumulonimbus base. If the cloud does not reach the surface, it is a funnel cloud. If it touches a land surface, it is a tornado, and if it touches water, it is a waterspout. Tornadoes occur with both isolated and squall line thunderstorms. Reports for forecasts of tornadoes indicate that atmospheric conditions are favorable for violent turbulence. An aircraft entering a tornado vortex is almost certain to suffer loss of control and structural damage. Since the vortex extends well into the cloud, any pilot inadvertently caught on instruments in a severe thunderstorm could encounter a hidden vortex. Families of tornadoes have been observed as appendages of the main cloud extending several miles outward from the area of lightning and precipitation. Thus, any cloud connected to a severe thunderstorm carries a threat of violence. Turbulence. Potentially hazardous turbulence is present in all thunderstorms, and a severe thunderstorm can destroy an aircraft. Strongest turbulence within the cloud occurs with shear between updrafts and downdrafts. Outside the cloud, shear turbulence has been encountered several thousand feet above and 20 miles laterally from a severe storm. A low-level turbulent area is the shear zone associated with the gust front. Often, a roll cloud on the leading edge of a storm marks the top of the eddies in this shear, and it signifies an extremely turbulent zone. Gust fronts often move far ahead, up to 15 miles, of associated precipitation. The gust front causes a rapid, and sometimes drastic, change in surface wind ahead of an approaching storm. Advisory Circular, AC 0054, Pilot Wind Shear Guide, explains gust front hazards associated with thunderstorms. Figure 2 in the AC shows a cross-section of a mature stage thunderstorm with a gust front area where very serious turbulence may be encountered. Icing. Updrafts in a thunderstorm support abundant liquid water with relatively large droplet sizes. When carried above the freezing level, the water becomes supercooled. When temperature in the upward current cools to about -15 degrees Celsius, much of the remaining water vapor sublimates as ice crystals. Above this level, at lower temperatures, the amount of supercooled water decreases. Supercooled water freezes on impact with an aircraft. Clear icing can occur at any altitude above the freezing level, but at high levels, icing from smaller droplets may be rime or mixed rime and clear ice. The abundance of large, supercooled water droplets makes clear icing very rapid between 0 degrees Celsius and -15 degrees Celsius, and encounters can be frequent in a cluster of cells. Thunderstorm icing can be extremely hazardous. Thunderstorms are not the only area where pilots could encounter icing conditions. Pilots should be alert for icing anytime the temperature approaches 0 degrees Celsius and visible moisture is present. Hail. Hail competes with turbulence as the greatest thunderstorm hazard to aircraft. Supercooled drops above the freezing level begin to freeze. Once a drop has frozen, other drops latch on and freeze it, so the hailstone grows, sometimes into a huge ice ball. Large hail occurs with severe thunderstorms with strong updrafts that have built to great heights. Eventually, the hailstones fall, possibly some distance from the storm core. Hail may be encountered in clear air several miles from thunderstorm clouds. As hailstones fall through air whose temperature is above 0 degrees Celsius, they begin to melt and precipitation may reach the ground as either hail or rain. Rain at the surface does not mean the absence of hail aloft. Possible hail should be anticipated with any thunderstorm, especially beneath the anvil of a large cumulonimbus. Hailstones larger than 1/2 inch in diameter can significantly damage an aircraft in a few seconds. Ceiling invisibility. Generally, visibility is near zero within a thunderstorm cloud. Ceiling invisibility also may be restricted in precipitation and dust between the cloud base and the ground. The restrictions create the same problem as all ceiling invisibility restrictions, but the hazards are multiplied when associated with the other thunderstorm hazards of turbulence, hail, and lightning. Effect on altimeters. Pressure usually falls rapidly with the approach of a thunderstorm, rises sharply with the onset of the first gust and arrival of the cold downdraft and heavy rain showers, and then falls back to normal as the storm moves on. This cycle of pressure change may occur in 15 minutes. If the pilot does not receive a corrected altimeter setting, the altimeter may be more than 100 feet in error. Lightning. A lightning strike can puncture the skin of an aircraft and damage communications and electronic navigational equipment. Although lightning has been suspected of igniting fuel vapors and causing an explosion, serious accidents due to lightning strikes are rare. Nearby lightning can blind the pilot, rendering him or her momentarily unable to navigate either by instrument or by visual reference. Nearby lightning can also induce permanent errors in the magnetic compass. Lightning discharges, even distant ones, can disrupt radio communications on low and medium frequencies. Though lightning intensity and frequency have no simple relationship to other storm parameters, severe storms, as a rule, have a high frequency of lightning. Engine water ingestion. Turbine engines have a limit on the amount of water they can ingest. Updrafts are present in many thunderstorms, particularly those in the developing stages. If the updraft velocity in the thunderstorm approaches or exceeds the terminal velocity of the falling raindrops, very high concentrations of water may occur. It is possible that these concentrations can be in excess of the quantity of water turbine engines are designed to ingest. Therefore, severe thunderstorms may contain areas of high water concentration, which could result in flameout and/or structural failure of one or more engines. Chapter Summary. Knowledge of the atmosphere and the forces acting within it to create weather is essential to understand how weather affects a flight. By understanding basic weather theories, a pilot can make sound decisions during flight planning after receiving weather briefings. For additional information on the topics discussed in this chapter, see the following publications as amended: ACOO-6, Aviation Weather for Pilots and Flight Operations Personnel; ACOO-24, Thunderstorms; ACOO-45, Aviation Weather Services; AC 91-74, Pilot Guide; Flight and Icing Conditions; and Chapter 7, Section 2 of the Aeronautical Information Manual, AIM.